Okay, so for these slides, I think someone said I did not do it. I decided now to do it and just re-emphasize because I thought I covered it. Okay, so for elimination reactions, you might end up with the double bond placed differently on the structure. That's called regiochemistry. It's a reaction that can occur with different regions on a molecule to produce different products. So like you see here, the double bond is within the structure, here it's outside. So regioselective reaction is when there is more than one reactive site where a regioselective reaction can occur giving different products. Okay, now assume that you have a strong base and the strong base happens to be small. So usually it's gonna go for the beta hydrogens that is sitting on a more substituted beta carbon, because you do have this other option of beta hydrogens which are sitting on a less substituted beta carbon. So if the base is small, like what we have here called an ethoxide, it's gonna really not care about taking out the most accessible hydrogen. It's gonna go for the one that's within the molecule, which is this one. Remember, beta carbons are bonded to the alpha carbon bearing the leaving group. They're just the neighboring carbon to the carbon bearing the leaving group. So take out that hydrogen, make a double bond. This leaves, you make this more substituted carbon. Let's see how substituted this is. You have 1, 2, 3 carbons surrounding the double bond. This is tri-substituted. Okay. Now, if the small, strong base forgets and takes out the other option of beta hydrogen, so let's take out one of the top one. You know, these two are metals, so we're gonna take the top one or the bottom one. If you take out that, make a double bond, this goes, you get 2 carbons across the double bond, you know. So this one is called, that's a CH2. This is called di-substituted. So in reactions where a more substituted double bond is formed, that's gonna be the major. Of course, you see the evidence. This is 71% yield. This is 29% yield. So this will be the major one, and it follows a rule that we call slides7 rule, which you'll see shortly, where whenever you're using small bases, you get the more substituted alkene. So when this is the slides7 rule that states when 2 or more alkenes can be produced in an elimination reaction, the thermodynamically more stable product will dominate. What is the thermodynamically more stable product? That's gonna be the alkene that has the most alkyl groups attached to it. For example, this one is tri-substituted, has 3 carbons attached to the double bond. This is di-substituted, has 2 carbons attached to the double bond. So this is taken to be the major. It's gonna be formed more after the reaction is done compared to this one, evidenced by the percentage yield that someone did in the lab. So again, if you're using a strong base which happens to be small, like methoxide, ethoxide, that will go for the red hydrogens which are sitting on a neighboring beta carbon that's more substituted. You see this carbon right here is a secondary carbon, it's bonded to 2 other carbons, while these carbons are primary carbons because they are bonded to one other carbon. These are less substituted compared to the secondary. A small strong base in E2 reactions or E1 will go for beta hydrogen sitting on a more substituted beta carbon. So the base will take that hydrogen out using this arrow. You make a double bond and then this goes. Notice that I'm taking out hydrogens that are 180 degrees apart to the bromine. That is the anti-coplanar rule that we talked about, or that's always explained in E2. So the product here will be, the major product will be this one, because obviously I see, once I make a double bond, I see 1, 2, 3 carbons directly bonded to the double bond. This is tri-substituted. Okay, now if it chooses to take one off one of the blues, you're gonna get this one, which will be di-substituted. For those who don't see how that's formed, let me show you. So I'm taking out the hydrogens in blue, the beta hydrogens in blue. So let's say your methoxide, the strong small base, comes in and takes out this hydrogen. That's 180 degrees apart in orientation to the leaving group. You're gonna make a double bond. So you take this arrow, shows that the hydrogen is removed. Use the bond to make a double bond. This falls off. That's how you get this. And this is disubstituted again because the double bond is bonded only to 2 carbons. According to this rule, the more substituted double bond will be favored. Okay. So whenever you have a bulky base, and I think this was recorded in another video, this will be the last slide I'm doing for this remedial. If you have a strong base, these are strong bases and alkoxides are strong bases, but this tends to be huge, bulky. You see now this time you have the CH3s, so it's bulky. Compare this base to a methoxide. All that the methoxides have is the baby hydrogens, right? So replace those baby hydrogens with alkyl groups, you get a bulky group. This will not have enough space to go take out this beta hydrogen that was taken out by a small base to give you the trisubstituted alkene. So instead, it's gonna take out the most accessible hydrogen, which is one of the hydrogens on the CH3s. That's why I'm modifying this CH3 to CH2H. It's going to take out the most accessible. So when that happens again, you get this product, which is disubstituted, but it's okay. It's okay. That's going to be the major this time because this base is huge, cannot fit into the pocket of the molecule to take out a beta hydrogen from a more substituted secondary carbon in this case. So instead, it's going to take out a beta hydrogen from a neighboring beta carbon, which happens to be a primary. The most accessible beta hydrogen will be taken out. Okay, that's called the Hofmann product. So there are times where the least substituted double bond is favored just because of the bulky base. All right. So generally speaking, to finish this off, according to this rule, if you have a small strong base, then the one that has 4 carbons around it, the tetrasubstituted double bond, will be the major, followed by the one that has 3 carbons around the double bond, which is trisubstituted, followed by disubstituted. For disubstituted, you either have what we call terminal or germinal alkene. You have 2 carbons, so it's still disubstituted. Then you have the disubstituted, which is trans, and disubstituted, which is cis. So most of the time the trans wins because the groups are further apart, minimize sterics, and the disubstituted will win over where you only have 1 carbon attached to the double bond, which is mono, according to Zaitsev rule trend. Stability of alkenes. The more the alkyl groups, the more stable the alkene is, the more likely it's going to be formed after a reaction, the more thermodynamically stable the alkene will be when you have the more alkyl groups attached to it. For example, tetrasubstituted has the most alkyl groups attached to it, is thermodynamically stable. We say it's thermodynamically stable. It's more favored, more likely to be formed after a reaction. So I think that concludes the few slides that you guys wanted us to discuss. Okay, so using this example, there's a carbon there attached to the double bond, there's a carbon here, this is trisub. We're trying to look for which one's more stable. There is a carbon there, there's no other carbon, this is mono substituted, and then there's a carbon, this is tetra substituted. So the tetra substituted will be the most stable over the tri-substituted and the mono substituted according to this rule.